This video is a summary of the exponential function. The parent function for this is of the form f of x equals b to the x. Basically, that just means it's any number that's greater than 0 raised to some exponent. In your handout that I gave you, we're just going to use 2 to the x just because that's like the simplest form that you can find. And I've already generated a table here, but I wanted you to see how I got some of these. All you're doing is replacing the x with these x values. So for example, if you put a 3 in, you would get 2 to the third. Well, 2 to the third is 8. If you put a 2 in, you get 2 squared, which is 4. If you put a 1 in, you would get 2 to the first, which is 2. And if you put a 0 in, you get 2 to the 0, which anything 2 to the 0 is 1. Any number to the 0 is 1. And it just goes on and on. For example, the reason this is a half is because 2 to the negative 1 is the same as 1 over 2, which is 1 half. 2 to the negative 2 is the same as 1 over 2 squared, which is 1 over 4. And then finally, 2 to the negative 3 is the same as 1 over 2 cubed, which is 1 over 8. So I'm just going to plot these points. So here's roughly the sketch of the graph of 2 to the x. As you can see, it gets smaller and smaller and smaller, and although it appears to touch 0, it never actually crosses this line. So when you are doing your domain and range, you have to consider that. The domain for this is going to be all real numbers. But for the range, since it never crosses over 0, the range is going to be from 0 to infinity, or simply y is greater than or equal to 0. The next function we're going to work with is f of x is equal to 1 half to the x. And if you look at the table I've already generated here, you could notice a couple of things. See how when you put in a 3, you get out, well, this is really 1/8, but 0.125. But when you put in a negative 3, you get out an 8. So look at how that is kind of switched over. So we'll go ahead and graph these points and compare the difference between these two graphs. You can see how the graphs are very similar, except they are just, it's just a reflection over the line y equals, or just the line x equals 0 actually, the y-axis. The domain is still going to be all real numbers. And the range, it's still going to get closer and closer and closer to 0, but it's never going to cross over this line. So the range is still going to be from 0 to infinity, or y is greater than or equal to 0. The next exponential we'll talk about is the natural exponential. And you're probably looking at this e and thinking it's a variable. It's not a variable. It's an irrational number, just like pi is an irrational number. E is just the symbol that it's used for. It's called natural because it arises in the field of math and science, in the natural sciences, naturally. It was discovered way, way long ago by a Swiss mathematician named Euler. And he swears he uses the letter E just because, for exponential, not for his name. But anyways, this is just something you'll run into, especially when you get to pre-calculus and calculus later on. But anyways, on your calculator, if you want to find the E button, it is right above, or actually to the left of the number 4. And it's also beside the natural log key. So if you want to look on your calculator, it's in blue, so you have to hit second LN to get there. And again, it's right beside the number 4. So anyways, I went ahead and generated a table, but you can go ahead and do that yourself by just simply typing this into y equals on your graphing calculator. So I'm just going to generate some points here, and I want you to compare it to the graph above. As you can see, the graph here is very similar to the graph of y equals 2 to the x, because the base is, very close to the exponent of, to the base of 2. It's 2.71. But it starts to see some disparity when you get to 3, because 3 you go all the way to 20, whereas on 2 to the x it was just 8. So it starts growing at a much faster rate. The domain is still all real numbers. And the range is just the same too, 0 to infinity, or y is greater than or equal to 0. Our next function is very similar to the one above. It's 1/2 x to the, or excuse me, 1/2 to the x minus 1. And notice it's just a shift. If you graph all these points, it's just a shift of the graph 1/2 to the x. And see if you can tell how it shifts based on this exponent. After you've compared these, do you see that this is just a shift 1 to the right? And that has everything to do with the exponent here. So whenever your exponent has more than just an x, like an x minus 1, x plus 1, it's going to shift it either right or left, depending on what the exponent is. And it's the opposite, again, of what you think. The domain is still going to be all real numbers. And it's still not going over this line, the line right here, y equals 0. So the range is still going to be from 0 to infinity, or y is greater than or equal to 0. For the summary of exponential functions, the domain is all real numbers. The range is 0 to infinity, or y greater than or equal to 0. And there's always going to be a variable x in the exponent. And the y values, they're either going to increase very, very rapidly, or they're going to decrease very, very rapidly. And this is also known as exponential growth and decay. And we'll get more into that later on in the semester. The next function we're going to talk about is the logarithmic function. The parent function is really f of x equals log base b of x, where b is always going to be greater than 1. We're going to use log x, and it has an understood base of 10 here. So you might want to just jot down that the understood base, if it's not written, is 10 if not written. So this is really the parent function, but we're going to put f of x equals log of x in our parent function space here. And if you go ahead and type that into your calculator, you do have a log button, and it's to the left of the number 7. It's LOG. So if you'll use that, you can generate yourself a table. And I'm writing these down. You're going to need a little bit of extra space because I want you to see where your calculator says error. So if you put this in your calculator, this is what your calculator says. And the reason you get this message here, this error message, is because the domain of a log function does not start until 0, and it doesn't include 0. So it's from 0 to infinity, or simply, I didn't mean to put y, I meant to put x is greater than 0, not greater than or equal to. I went ahead and added some more points so you could see what's going on with the graph over here. If you look at this graph in your graphing calculator, it's going to look really weird. It's going to look like it doesn't even go past this point here, but it does go down pretty rapidly, but it never crosses over that line. And then over here, you can kind of see how at 1 it's 0, at 2 it goes up just a little bit, at 3 it goes up a little bit more, at 4 it goes up more than that. But it doesn't reach 1. It doesn't even reach 1 until 10. So 1, 2, 3. So right here. And it keeps going forever and ever right and forever and ever down. This time the range is going to be what's all real numbers. And you can see that this graph is going to continuously go down, and it'll be going up, but really, 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 really slow. Our next function, is the natural logarithmic function. It's ln, but you read this, the natural log of x. It has an understood base of e, just like we talked about in the exponential video above, or just before. It's understood to have a base of e, but it's just not written. So it's the natural log, whereas e to the x is the natural exponent. But it's very, very similar to the log of x. There's also a button on your calculator for this one. For the table for the natural log, I just started with 1. You're going to get the same error that you did for the natural log when you go to the, for log base 10 of x, as you do for the natural log of x. The natural log button is located to the left of the 4 on your calculator. It says ln. So you can generate this table on your own also. So I'm going to go ahead and graph this, and you can compare and see how closely they relate. As you can see, the graphs are very, very similar in shape, but the natural log is, the y values are going to increase a little bit faster than the y values of the log base 10. The domain is still going to be 0, not including 0, to infinity, or simply x is greater than 0, and the range is going to be all real numbers. The next function is log base 2 of x. So since there's a 2 written, it is what it is. So if it wasn't a number there, it would be log base 10 of x. But this is log base 2 of x. And you can use your calculator for this also. To get to where you can change the base, you hit math, and then you go all the way down, scroll all the way down to the letter A, and it looks like this on your calculator. It looks like log, and then they capitalize base. And if you hit that button, you'll get a prompt, and it will look like this, and you'll just fill in everything. So if you want to generate a table, you'll just hit math, then log base, which again, you have to scroll down pretty far, and you'll get this prompt, and you'll just put in a 2 here and an x here, and you'll be able to generate this table. And the graph will look something like this. You have to be really careful when you look at these graphs, because it does look like that it's not, that it's stopping right about here, but it does continue to go down. So the domain is still 0 to infinity, or x is greater than 0, and the range is still all real numbers. So the only thing that's changed really is just basically the shape. For our next graph, it's the log base 10, it's understood base 10, of x minus 2. And notice that this produces an error for 1 and for 2. This is because the log has been shifted, and no longer is your domain going to have have a 1 or a 2. It's going to actually start at 3, 0, and then it will continue the same pattern that you've noticed before. The domain for this graph is going to be from 2 to infinity. But notice it's not including the 2. So x has to be greater than 2. It can't be 2, it has to be greater than 2. And that's because the log, you can't have a log of 0. It has to be greater than 0. So basically, whatever this is has to be greater than 0. So the x's will have to be greater than 2. Now the range is still going to be all real numbers. So this has basically shifted the graph over, shifted right 2. Again, it's the same pattern that we've noticed. It's the opposite of what you think. So it shifted to the right 2. Just a summary of some of our findings. The domain is always going to be x is greater than 0, or from 0 to infinity, unless, of course, it's been shifted like we talked about this one. The range is going to always be all real numbers. Logs have an understood base of 10. So if there's nothing written, it's understood to be a 10. But if there's something written, of course, that's the base. And for a natural logarithm, it has an understood base e for the natural log. And again, the e is just an irrational number, just like we talked about with the exponential functions.